Alright, in this video we quickly go over what is meant by a surface integral of a vector field. And here is the notation for that surface integral. Capital F is the vector field, and S is the surface. Okay, and here is the notation that is used. Okay, this is a kind of a shorthand notation. There is a little bit longer notation that kind of discusses what is meant by dA. And dA, we can see from this notation over here, is n d sigma. And n is the unit normal to the surface, which means that it is the vector RU cross RV. But to make it a unit vector, we had to divide by the magnitude of RU RV. And we already know the definition of d sigma, that it is the magnitude of RU cross RV du dv. So we can see here that the magnitudes cancel out, and this tells us that dA is equal to the cross product of the partial derivatives of the surface with respect to the parameters du dv. Okay, so if we're writing out the notation here, that the meaning of, there's a notational meaning and then a physical meaning, that if we are looking at the vector field F dot producted with the surface area element across the surface itself, S, that what this means is that we need to find the vector field, evaluate it at points along the surface, and then do the dot product of that with RU cross RV, and then integrate that result over U and V parameters. Okay, so the meaning of this integral, we can go into that a little bit now. We're seeing here in this picture RU cross RV. We need to do a dot product with that quantity. We're familiar with this quantity. This is the normal vector to the surface. So at every point on the surface, there is a normal vector at that point. So that is n is equal to RU cross RV. Not necessarily a unit vector in this case, but the vector that points in the direction of the surface. And that is tangent, each of those vectors is tangent to a little part of this surface at this point. So there's a little tangent plane, and each of those vectors are tangent to, normal to the surface. Okay, so there is the vector n, RU cross RV. Okay, not as a unit vector in this case. And then we have to introduce the vector field itself. Okay, at each point on the surface, there is another vector called the vector field. This vector might change depending on what the vector field is, but let's say we have these vectors F. Okay, so here's the vector field, and because we're looking at the points on the surface, we might call this the vector field evaluated at the points on the surface. Okay, and then we're familiar with this dot product. We know that when we compute a dot product, F dotted with RU cross RV, we're familiar with that dot product operation is the magnitude of the vector field, magnitude of RU cross RV, and then times the cosine of the angle between them. So there is an angle right here between the vector field and the surface itself. Okay, and when we do that dot product, we find the component of the vector field F that points in the direction of the surface. Okay, so when we're looking at these vector fields, only part of the vector field is pointing in the same direction as the surface. There is another part of the vector field that is pointing in the same parallel to the surface. Okay, so if we look at the vector field at every point, the vector field here part of it points in the direction of the surface. That's this black arrow there. But then there is another part of the surface or vector field right here that is pointing parallel to the surface. Okay, so what we're going to do in this double integral of a vector field across the surface is look at how much of the vector field is actually coming through and passing through the surface. How much is pointing in the same direction as the surface. Okay, and then we are going to do an integral which adds up all the amount of the vector field passing through the surface. Okay, so in terms of units, it might be a good idea to think of the vector field, for example, as as a flow field. So maybe we have a field which is saying how many liters of a fluid per meter squared. So we have a flow rate, right? So the vector field might come out in liters per meter squared. And dA, because of its definition here, dA is going to have the units of d sigma, which has the units of meters squared. So liter per meter squared times meter squared will indicate that the whole integral itself has the units of liters. So here, if we want to figure out how much of the vector field is actually crossing through the surface, and we want to accumulate all of the different, the amount coming through the surface, given that, at each point you may have a flow, there may be less fluid flowing through this part of the surface at this point. You may have a vector field that points this way, so none of the fluid is actually passing through the surface because they're at right angles. The vector field and the surface could be at right angles. So one thing that we're trying to do with this double integral is add up the contribution of how much the vector field F crosses through the surface. And to do that, we always need to project the vector field into the direction that the surface is pointing in. And that's why this dot product is right. That's why this dot product is here of the vector field with the surface direction itself. Okay, so here we get this type of integral is called a flux vector field. Sorry, a flux integral, I mean to say. All right, so ends this introductory video.